Okay, today we're talking about generative model, probabilistic graphical model as a big part of it, but also the neural generative model. The objective today for the lecture, there are three main parts to the lecture today. One is maybe because of my personal background, but I believe that there's a lot to gain with, we talk about neural architectures in the past few weeks, but there's a lot to gain with graphical models. The main thing is that it allows you to bring domain knowledge into your architectures. And some of the architectures or some of the things we see in neural architecture were in fact inspired originally from early versions in probabilistic graphical models. So I want to take a moment to really understand this, both from a probabilistic perspective and also from a design perspective. We'll focus today on one type of probabilistic graphical model, the family of Bayesian networks and dynamic Bayesian networks. And so that will be the focus. And next week, we'll also go further into discriminative graphical model like conditional random field and those energy models. To stay in the generative, I will also talk about the generative adversarial network as a neural, and it's a little bit of an interesting way because the way we use the word generative in this case, the meaning is slightly different from the, I would say, classical way we will be using in machine learning and probabilistic graphical models. I would clarify these at the same time, but it would be an interesting not an exactly direct extension, but it keeps a lot of the same philosophical view on generating data. Let me start first with probabilistic graphical model. What is a probabilistic graphical model as a first step? A probabilistic graphical model is a graph representation. It's a formalism, like the graphical model is a formalism, a way almost to represent both mathematically and visually and a compact modeling of the joint probability distribution. And what's interesting in this is that the same graphical models will often give you this compact modeling, but also will give you dependence of the structure, like dependent structure. So, and we'll discuss some of it in this. So this is this is a generic definition of this, but in this case, like to start and go in more details. We talked about it about 3 weeks ago about random variable. You remember there were discrete and continuous random variable, but there's also a probability distribution defined over those random variable. But for the purpose now, I would like to focus on one specific type of probabilistic distribution, where the one that looks at the joint distribution of all the variables that are present into this. And why is it so important or so interesting, like spending all this time to learn the full joint distribution? Like if you have many random variable, like you're trying to, I don't know, predict the emotion, and you have language and acoustic and visual, why will you spend this whole time learning the full joint distribution and not maybe just the conditional distribution, which maybe in certain cases maybe is easier? And so what gives you to do the full joint distribution? When you learn the joint distribution, and if A, B, C, D was each is random variable, at least for the beginning now, I will look at them as discrete random variable. It's a little bit easier to explain, but as we saw 3 lectures ago, a lot of the theory that you see for the discrete, which often these distributions will be represented maybe as a matrix, then these will be, in the case of a 5-dimensional or 5 discrete variable, then it would be 5-dimensional matrix, like a 5-dimensional tensor. So when you see a joint distribution like this at the basic, imagine right away P of this right away it should be, and if each of these random variable is one dimension by itself, right away you should think 5D tensor. And one thing you get from that 5D tensor is like any element in that 5D tensor, any of these elements is in fact a probability, and it's a probability of a specific joint event to happen. Like the joint event will be A equal 1, B equal car, C equal 2, D banana, and E equal 10. Like this is just example, but the interesting part is A maybe could go from 1 to 5, B could be car, bus, airplane, and C maybe 1 to 10, a banana, and then you could have other meals, and then 10E could go maybe also to 10. So this is your space. That's what a joint probability. And I just hinted about the word generative model. A generative model, at least one definition for a generative model, when we say generative versus discriminative model, one way to see a difference is to say the generative model is modeling the joint probability. And often discriminative model will look at it and optimize more of the conditional probability. That's one of the way of formalizing these two differences. So that's the kind of, when I talk about joint probability distribution, I'm also thinking about generative model. And so this probability here will be a specific entry or element in that 5D tensor. That's one thing when you learn a joint probability. But once you learn the joint probability, if you have this whole tensor, then you can start doing very cool thing as well. You can also look at conditional probability with it, because you have the whole joint probability distribution model. You can go and model like a query. So I'm going to define a few terms here, but here a subset of the variable, we're going to call them a query. And then given some known assignments, so these are the known assignments. So, oops, sorry, I just saw my sense. Okay, these are the queries, and these are the known assignments. And so, and then there are some other variable, which I will discuss in a second, because here I have A and D and C, but the joint distribution was also over B and E. And so what will happen is B and E, we don't really care, like any of these values are okay with us. So we will just like marginalize, we'll just like sum over them if they're discrete, or just integrate over them if they're continuous. So that's one aspect of these kind of query or conditional probabilities that you can get from a joint. But how to really solve this completely, it's not just about B and E. So the first part is about the marginalized, but the second part is that we have this conditional probability, like, so these events are known. And so if we have those known events, then we can use the inverse product rule. And then we can now, if we use that inverse product rule, then we get that joint probability that we already have in stock, and we can use just divided by the prior on all of the assigned one. And so you can nicely, now we can have the joint probability. And so this can be seen. What you see here is you integrate, you marginalize over the variable that were not part of the query. And then for the ones that are known, then they're simply divided by the prior for them. And in more generic terms, like to have it, so you have the X, which is the query, the Y, and so it could be more than one variable, but X could be more than one variable, Y could be more than one variable. And then we have the joint probability that will be marginalized for all of the variables that are not part of X and Y. And then the alpha here is the one that will, it's the constant, but it's the one that will be where all of the prior, or one over the priors, will be there. So, but the question now, so it's very useful to have the joint probability. It's a very powerful tool, and for being generative after that also to generate data, but it could be also for queries like we just mentioned. So, but how can we if we have only 5 variables, maybe a 5D will be okay. But if we have like 1,000 variable or 100 variables, like then these variables will like to model all of it explicitly, all these interaction explicitly, maybe too large, or we're not really taking advantage of the knowledge that we have. So there may be some knowledge we know about the problem, and that's where the graphical models will come in, is that we would like to take that joint probability and try to make it a little bit more compact. Compact meaning there will be more terms. It's like, it's not going to be maybe just one big giant terms, but it's going to be more terms, but each of these terms are going to be simpler. Much simpler, like much smaller matrices or tensors to represent that distribution. And so for 2 variable X and Y, the extreme version of the kind of knowledge you could have is you could say, hey, these 2 variables are just independent, 2 independent variable. And that's one way you could go. And in which case, if you have the joint probability of these 2 variables that are independent, then if these 2 variables are independent, then that what you know from that is that if the P of X given Y, we know that if P of X given Y, if they are independent, then it's the equivalent about P of X, because even if I know everything I know about Y, it still doesn't change anything. It's still the same probability for X. And so you can just use the same rule we used earlier, and then that knowledge about independence can be then used to simplify the joint probability. So P of X and Y is this. And so this is probably one you already know, and that's something that can generalize for any number of independent variables. The more interesting one is conditionally independence. So if I have a variable X and I already know Z, if I already know Z, and maybe I also want to know Y, I already know Y. In this case, just knowing Z is enough. Whatever the Y is, as long as I know Z, if I know this, I know its value, in that case, then there's no influence from the Y. So this is conditionally independent. So taking these 2 rules, very simple rules, now we can start taking any problems and try to show it graphically. And that's what the graphical models, and the graphical models will usually have one-to-one with the mathematical formalism. And it's a tool to visualize those conditional independence. And there are different, the generic kind of graph, or there's some simpler version of that, like a chain will be the simpler one. It's a simple sequence. You could have cycles in it. So these are different kind. Today we'll talk about Bayesian network, which look at directed acyclic graph. And really model the conditional dependency. And the Markov one, although will not model explicitly the conditional dependence, but will allow us to also model cyclic dependencies, and this will allow us to look at the formalism for that would be through the undirected graph. But it's really abstract, these graphical models, and for first-timers, and so I'd like to really give you an example. We're going to build, like train your own dragon, like build your own graphical models, and for that I will use one example. It's a relatively simple example, but it's a nice step and that will also give us the idea that there is knowledge you know about the problem, and we're going to use that knowledge about the problem to be able to create a hypothetical model for this problem. And if you have many hypotheses on how the model could be, how the problem could be solved, then you could end up having multiple models. And the same way we have hyperparameters, you could have multiple model, and then you will do model selection on all of them. That's one way you could do that. So the problem here is you want to infer from looking at the behavior of the student, like all the data. And this student, let's say, are interacting with a tutoring system. Tutoring system will be maybe an online system that is helping you solve a problem, mathematics problem or chemistry. And the goal here will be to estimate the emotion. So from looking at how the people, the student are interacting with the system, and maybe also you have some extra information about the student. Maybe you have their personality information. So using that personality information, or using like all of the information you get from the system, like all the logs, like what did the person click on? Did they go quickly in answering the first answers? Can I infer the emotion? The equivalent to that will be, I'm not suggesting you should, any company should be do this, but like, let's say you have on your cell phone and you get from the typing from which app is open and try to infer which emotion the person is. That will be, so you can see it's a very indirect. I mean, you don't see directly the facial expression. You don't see directly, the person is not expressing their emotion directly. You get from indirect. So it's a very challenging problem. And for these kind of very challenging problem, you may be lucky and you have millions and millions of examples, in which case you go data driven, like neural architecture maybe. But here you may have only like 1,000, maybe even 500, 1,000. In this kind of situation, you should think about visiting these problems, these Bayesian. So let's work together and let's find, how can I detect emotions, like one of those 7-class emotion? And the only thing I will have as input are the logs of what people did, like how many books they've seen, how many notes they took, how many posts they've seen, and maybe also how many correct answers they had, how many incorrect answers, total goals they reach. And maybe also I have something about their personality, and just in general, maybe there's some interesting metrics related to everybody. When they think about personality, maybe think about the 5 personality, big 5, like openness. But there's also maybe something about how much this person like or want to avoid mastery of the approach in general. So how do I go and predict emotion? Let's put our very big engineering hat and say, or machine learning, or one hat, I don't know which hat it is, but like one simple way to go is to say, hey, let's connect everything to everything. I could take all of my features, that's what I have, and go data driven. And I say, with enough data, I should be able to learn any kind of latent structure that exists between my input and my output. I just go data driven. Or I may be lucky and I have some pre-training, I can pre-train on one. But these are not the kind of features you've seen every day. And so you're less likely to have like a huge amount of data. But emotion, there's some knowledge about emotion. People have been studying emotion. Let me teach you in like 30 seconds or a bit less, one theory of emotion that I personally like quite a bit. And if you are studying emotion, you should probably study appraisal theory of emotion, going beyond this kind of arousal balance view of emotion and really study appraisal theory. And appraisal theory argues for importance of 3 interrelated concepts: the world event, the mental state, and then the emotional response to it. And so I'm going at very like high level. The idea is that the emotion is a product, an output of an appraisal of like, hey, let me understand, like what is my mental state, what is the world, and based on that, and based on that assessment, then the emotion is almost like a response to that appraisal. And so that's one theory that says, hey, let me look at the world, let me look at my personal goal. And so an emotion can be because of something that I appraise from outside, just by itself, or often it's something that happened outside, but I have my own goal and how well they're compatible with each other. So if they're not compatible, then maybe I will have more of a negative emotion at that point, or surprise. So you can see, or if they align with my expectation, but maybe at that case, I will be happier. And so in that sense, if we know two of these variables, we can make the prediction. So the environment and the mind give you a response. So this is a very high level view of theory, but that also tells me if I have goals, like if there's something I want, and that's on one side, and then on the other side, if I reach it, then the two of them being compatible, then maybe the emotion is more likely to be positive. If I try very hard something, but I don't get the result, I'm probably going to get really negative. Another interesting thing, if I do nothing and I get nothing, maybe I'm just happy with it, and it's not so negative in itself, because I barely did a little bit, and then I just got nothing. And so the idea is that let me try to see from all these variables, can I start operationalizing it? So maybe my emotions are really based on that positive versus negative, like that tells me were my goals and what I did were the same and aligned. And so in that sense, I can appraise, like, how much did I want to learn, and I did actively, and how well did I perform, and from these two, if they're really compatible, then maybe then I will be really positive. And what will change is probably also my mastery of it, like how much do I know about the topic and how much do I want to focus on. So all of these together, so the balance will be like this compatibility between the two, like, is it positive? It's like, did I really want to do something, and finally and I didn't get it, then I would be very negative. And if I didn't put energy in it, then I didn't perform well, then maybe it's still positive. But the emotion may be going a little bit further, is like the aspect of focus, like how much you master something. And my personality can also balance, because if I'm maybe someone who is really conscientious, and that will maybe also change on how positive or negative I am based on this. So what I just did is created a Bayesian network based on a theory, and I use that theory to inspire this. And now you could say, hey, why is the focus pointed there? Why is it not pointed to balance? I got this hypothesis that it was this way. Now, if you ask, you could do model selection, and you could do one with the focus where it's there and one where it's unbalanced. That's another possibility. That's called the same way you will select different hyperparameter. You can also do it for the model selection. But I have an opportunity to put knowledge. And I want to add one more thing, is that these Bayesian network could be dynamic, like, because right now for this lecture today, I spent a lot of time, so I got good performance. But maybe next week, that can also have an impact, or from day to day, or from hours to hours. So my balance will also probably be dependent on my previous balance, and my next balance will be dependent on each other, on my previous one, and maybe the emotion as well, although this is debatable if you would want to have just the balance to be modeled between time step, or you would like also the emotion to be there. And so this is a dynamic Bayesian network that I just created in front of you. This is just a different representation of the exact same dynamic Bayesian network. My balance is having an impact on my emotion, but my balance really comes from my performance and my learning balance. Like, so, like, how much do I spend energy, and how much energy I spend and how well did I perform will have an impact on my balance, but also how much do I focus in general, and then also my survey will also have an impact, like how not that survey, but my personality will also have an impact. And this exact place and that work in the world of emotion, the percentages are sometimes lower, but then you get something that's improving because you got knowledge that you added, and so that allows you to learn from a limited amount of data, and also the dynamic aspect to that. So this is your first example, building your first Bayesian network. I invite you to try it in your work. Try to take maybe some interpretable features as input, and take maybe one of your label and try to think about how can I build a Bayesian network with this. Let me formalize this thing that we just did in mathematically, because I emphasize the graphical, but I want to also emphasize the mathematical aspect of it. So by definition, Bayesian network, it's a simple graphical notation for conditional independence assertion, and it has for compact specification of the full joint distribution. So this is things I already mentioned, looking at the conditional independence and trying to make it more compact. By compact, it doesn't mean that, like, if you write it down, it doesn't look compact, maybe because there will be many terms, but it's compact because each of these are very small probability distribution, which we'll discuss in a second, what they look at. So, but just notation wise, or you could call it syntax, but notation, it's a set of nodes, so a set of random variable, and then it's a directed graph, and usually we try a cyclic graph, at least, otherwise you have pseudo. The inference will be more challenging, and then you will these nodes, each node will have a conditional distribution associated with this, and this will be defined by its parents. The conditional distribution will be defined by the node itself and its parents, not by its child at all. So in the simplest case, conditional distribution represent the conditional distribution given the over X for each of the parents. And so let me give a little bit of details on that. So Bayesian network, this is just an example of that, but of a directed graph, and we did one of them together. But let's do one like more, just because I'm gonna use it also mathematically to show you this one. So I'm at work, neighbor John calls to say my alarm is ringing, but neighbor Mary doesn't call. Sometimes it's set off by minor earthquake. Is there a burglar, like a thief? So first step of building a neural network is to define what are your variables. What are your variables in this case? I have John who calls. There is Mary that could have calls. There is a minor earthquake. There is the alarm that's ringing, and there's a burglar. So there's like 5 of these variables. The more interesting thing is, like, what are the I will call it causal knowledge, but with big quote, just for, but the knowledge here, what is the knowledge I have? From this, I know that if a burglar can, I know that a burglar can set the alarm off. I know that an earthquake can set the alarm off. These two are possible. I know that if the alarm is happening, it can cause Mary to call, and if the alarm is happening, John can call. So if I get this, what are the network topology that I will have in this case? It will be like burglar. What is the link between alarm and burglar? Is that like if the burglar is happened, then there's likely an alarm. So that's the knowledge I have. And so P of the alarm given burglar, that's the kind of probability that I will know, distribution probability that I will know and want to learn. And so alarm and earthquake, that's the knowledge. If I know that if the alarm is happening, the earthquake is happening, the alarm is likely to happen. And if the alarm is happening, it's likely that Mary calls and alarm John call. And I say likely, I probably spoke quickly here. It could be likely or unlikely. And that's because because that's what the probability will tell me. The high probability will say mean that it's very likely, and low probability will be that it's really unlikely. But for this kind of example, what's really nice is that we can, once we got that joint probability, we can go and use all these conditional probabilities to go and simplify a little bit the problem, or making it more compact. So one way to do it will be to just use the chain rule, not even like take this and just take the chain rule. And that's something I could do without any knowledge, is to just go ahead and do any chain rule. And that's like arbitrary. But here, what it is we want to take advantage of the graphical model. And so there are things we know. There are some variables that are independent, and there are some of them that are conditionally dependent. And so I want to take advantage specifically of the conditionally independent. And there, in a Bayesian network, each conditional probability for a specific variable only depends on the parents. So for this variable y only depends on the parent being who points to me. And that's a really nice simplification, because now I can take this joint probability and use and simplify it by using all of these conditional probability. And so for a conditional probability distribution, just to give a high level, given a variable x and its parent y and z, the conditional probability of the x given its parents. And so if it's categorical, it's simple. It's just a matrix where you set, given that y was 0, that let's say that y is the parent, y is 0. What is the probability of x be also 0? Or what is it the probability of 1, x being 1? And as you know, these should be summing to 1. And then on the other side, if y was 1, that's the parent being 1, and then these will again need to sum to 1. These can also be continuous, or variables are continuous, then you have multivariate. And for example, if they're continuous and multivariate, you can look at normal density function, or it could be just one continuous one. You could just look at Gaussian distribution for that as a way to approximate the continuous variable. So a lot of time these either based from data or from assumption, if they're continuous, we'll make another assumption from a design perspective on deciding which kind of probability distribution is likely to well model this. And if you don't know, I mean, some are that allows you to make no assumption. That's the extreme case. Or one thing is to just plot the relationship between y and x and plot it and see, does it follow like a Gaussian distribution? And so for our earlier example, this is like the full joint distribution can be summarized by 5 very simple tables. This like 5D tensor can be simplified by via simpler distributional probability distribution. So in the case of burglar, it doesn't have any parents. So then the only thing is about the prior. And here I only put the prior for b equal 1, but there's also another value which is b equals 0. That's kind of implied. I didn't put it just because for simplicity. And then the same thing for earthquake, doesn't have any parents, but here it has a parent, so it has it. Then there's 2 parents, burglar and earthquake, and each of them could be true or false. And in here, for each of these cases, then I will learn the probability for the alarm. And then if I given an alarm, then I can also look at the probability. And you can see it's a lot more likely that John called me if there's an alarm than Mary. That can also help me explain. So this is joint a probabilistic graphical model and looking at Bayesian network. I just quickly wanted to point out that there is this is kind of a side thing, but a very, very, very simple model will be a Bayesian naive-Bayes classifier. In this case, there's only one set of conditional distribution, conditional probabilistic distribution between the labels, which could be multivariate, but in this case is only one dimension, and the evidence, which is also could be multivariate. And so the score function, if you remember, from a second week, and so you can use the Bayes theorem from that, looking at the score function, and you can use it. And there you have the prior, the likelihood, and the posterior, and the marginal. And the marginal is just simply marginalizing over all of the y, so all of the possible labels. And that is just a naive-Bayes classifier. The real thing I want to talk about was the dynamic Bayesian network. Is a step further, and also start looking at multimodal extensions of that on this, because that's quite interesting to look at the multimodal. Although now these days, where a lot of people go with neural architectures, and in recent years people have not used graphical models as much for neural for multimodal. But what's really interesting is a lot of the concept that you see in multimodal neural architectures, in fact, were inspired from early on from some of these architectures that we had in graphical models. So the dynamic Bayesian network is a Bayesian network at its core, but it allows to represent sequential dependencies or temporal, if your data is temporal, or just sequential dependencies. The typical dynamic Bayesian network will have what's called a first order Markov assumption. First order Markov assumption is sometimes I make the joke, it's a little bit like Finding Nemo, like there was this fish that had a very short-term memory. It only remembers its current state and maybe not all of the other observation they had previously. So they will have their current state, their current knowledge up to now, but the previous observation will have been forgotten. Only the state is remembered. And so that means that the current state has to be able to summarize everything that has been observed up to the past. That's the first order. Second order means that you're allowed to go 2 times before, and then you can imagine there's extension to that. The interesting aspect, dynamic, is that like in an LSTM, it can change and evolve over time. And it's directed, so it's in a sense it's a feed forward from left to right. If you want, if you were to put it in a word of a neural representation. So an example here is that at each time step, it's the same Bayesian network usually. It's the same Bayesian network, the same random variable. It's just that I will add this like recurrence, like it feels like a recurrence, a little bit like a recurrent neural network. And so you will add these, and this is also by design, like because of knowledge, you will know which variable are likely to have a dependence between them. And so that's what you will want to model. If there's no thing in between two variables, then you think they are independent, or at least conditionally independent. And so the most famous of these dynamic Bayesian network, what is probably the most famous? People in speech will know the answer. It is the hidden Markov model. The idea here is that I have my observation, my evidence, and if you look at just this part, this looks a lot like naive Bayes, but the difference here, often the hidden Markov model will be done in such a way that it is not observed, like H will be a latent variable, something we're looking to. And if you ask me another way to look at this model, clustering. Think about it almost as a clustering, like this part. This part here is almost a clustering. So X, maybe all the spoken words in the world, let's say, and H. This H, what is H? H is a random variable. It can take usually numerical values from 0 to 20, let's say, or from 1 to 20. And it's a generative process. So the word needs to have been generated from H. And H can take only one of a discrete state, 1, 2, 3, 20. So you could see as H as a clustering machine, and in fact, it often implemented with the Gaussian model. Maybe if these were continuous, you could have say the conditional distribution could have been modeled with a Gaussian model, with you could imagine just clustering. So the cluster mean if H equal 1, what are the words that are likely to be generated when H equal 1? What are the words that are likely to be generated when H equal 2? What are the words that are likely to be generated when H equal 3? That's one view of these hidden states. They force something that could be very high dimensional. They force it to be this only random variable that is often discrete random variable. So hidden Markov models, and a lot of when we look at other graphical models like conditional random field, a lot of these variables, like these either latent variables or even the sometimes observed variables, these latent or observed variables, they often can be used as a way to cluster, to summarize the information. And so if you look at this, it says, hey, if I was to generate the yellow house closed, that's a weird closed, that's a bit of a weird English sentence. What is the sequence of states that will allow me to make it most likely to generate all of these words? That's what the hidden Markov will try to infer when looking at it, like from an inference perspective. And we'll look a little bit more next on how to optimize these, and you can also look at this as we'll discuss some of it a little bit more on the optimization part next week. But the interesting part is I have some observed. So I have 9 random variable, and 4 of them are observed and 5 of them are non-observed. And the idea is if I'm able to infer the joint probability of this, or if I have a model with a joint probability, then I can start to be able to say, what is probability P of H1 given X1, X2, X3, and X4. So that will be one way, and that will be marginalizing for H1. Or you could define this as P of H0, H1, H2, H3, H4, given X1, X2, X3, X4. And you can imagine that if I've learned my joint probability, I can answer that question. It's a typical query that you do. But what if I have multimodal data? What if I have multiple stream of data? And let me share with you some strategies of factorizing that this. And in fact, the first one is called factorial HMM. This one is not a multimodal in itself, but it's an interesting view. And here it says I only have one stream of observation, but I have, in fact, generating this stream of information, I have more than one process, more than one factors that are generating this. So that is an interesting extension. Now, what's interesting is to go even further and to look at it for more multimodal